Satellite launching. So this is the process of placing a satellite in a geostationary orbit. In a geostationary orbit. So we're going to have a sketch of this. Synchronous transfer. Geostationary orbit. So this we have as the satellite orbit. Satellite orbits, and we have the voltage required. Velocity 1, velocity 2. So when you look at this diagram, this is the satellite and this is the geostationary orbit. So we have said it's a process of placing a satellite in a geostationary orbit. When you look at this, the satellite is moving around this area, its orbit. This is a satellite. Then we're able to move it. This is the velocities at which it's able to maintain the satellite in the geostationary orbit. So you have the velocity v1 and the velocity v2. So also here we're going to realize that we still have the apogee and the perigee the way it is. So this process is, if we have used a diagram, this is how we figure it out. So because of the issue of balancing, then you have to have the velocity for transmitting and velocity for maintaining. And remember, this thing is in a space. So you have to use we also mind of the centrifugal forces that are going to put in place here there. So the process. Number one, we put the satellite in an inclined orbit. Put the satellite in an inclined elliptical orbit. In an inclined elliptical orbit, normally referred to as apogee. Normally referred to as the apogee at the geosynchronous orbit. Normally referred to as the apogee at the geosynchronous orbit. Process number two is at the transfer orbit at the transfer orbit. At the transfer orbit, apogee, yes. At the transfer orbit apogee. Then a rocket engine, AKM, a rocket engine. We will refer to this as AKM. Apogee kick motor, AKM, which stands for apogee kick motor. Apogee kick motor puts the satellite, into the geosynchronous orbit. So we are going to have, this is a satellite power system. All satellites require to be powered, and in this case, because we cannot have the power lines mounted in space, we're going to use mostly the solar energy that's captured with the solar cells for us to have that. So we're going to do this with the aid of a block diagram so that we are able to figure out exactly what happens. So in this case, you draw the block diagram first. This is the solar cells, solar panels. DC to AC inverters. Then we have the AC to DC. AC to DC rectifier. Then have the voltage regulators. And we have the DC outputs. This is the DC output. So between the solar panel and the DC inverter, we only have the batteries for storage of charge. So we connect the batteries there. Batteries. So the batteries, we have current flowing in two directions. So this what it is. So look at this. The solar panel is able to capture the solar radiations, and in the process of connecting the same power supply through the other system, the batteries get charged for backup purposes. So that in the event or during the evening when there's no sunlight, then we are able to have the battery supplying the entire system. When you look at it, the solar now provides a system where we are going to power the satellite throughout. So during the day, you are able to use the direct electromagnetic waves from the sun, but during the night hours, then the batteries is able to support the entire system. So through the batteries, we supply the DC, and that one is rectified. When you also look at this, is that we have the DC to AC, so that AC to DC. The reason for we have this is for purpose of stability. And because we need high voltage or high power supply system, you have to convert the DC to AC for purpose of step up the voltages to high values, then rectify those high value voltages to DC so that we get enough power to supply the entire system of the solar system. So the solar cells absorbs electromagnetic rays. The solar cells absorb electromagnetic rays from the sun, absorbs the electromagnetic rays from the sun and converts the energy into DC voltage and AC, and converts the energy into DC voltage and current for charging the battery. As well as supplying the satellite system the DC is converted back to AC using inverters. The DC is converted back to AC using inverters so that the AC voltage can be stepped up for adequate power requirements. This is because power transformation is easily achieved in AC form. So we have converted that. When you also look at that, the AC is converted back to DC. The AC power is converted back to DC to supply it's going back to DC to supply the satellite equipments. So lastly, the voltage regulator stabilizes the output. The voltage regulators stabilizes the output to the required values for operation of the satellite system. So we're going to have what I refer to as a satellite orbit and attitude. control. Satellite orbit and attitude control. So attitude control is the process of ensuring that satellite remains with the solar orientation. So the attitude is the process of making sure that solar orientation is within the space. So you can have this is attitude control is the process of ensuring the solar orientation is within the space. So we are going to have the block diagram for us to be able to explain this in details. This can be propulsion system. This can be sensors. This is attitude control. Antenna control. Control the orbit control. How that? We shall have this sensors will be able to connect to it. Station command. So you can look at this diagram. Is a solar orbit and attitude control subsystem. And when you look at this diagram, we have the propulsion equipment, we have the sensors, the attitude control, the antenna control, and the beetle control. When we look, how this thing works is that anytime you want to maintain the solar orientation within the space so that we're able to absorb maximum energy, the sensors determines or detects the low values that in terms of power and is able to devise, is able to the sensor detects the low signal received and is able to improve the power or increase the power so that the antenna is rotated, so that we get the proper orientation as required as required by the Earth station. Another thing is that when the sensor rotates, there's normally an Earth station command signal that provides us the reference source, so that this part of it is able to give us the reference source and the sensor is able to work based on the reference source. The difference is what actuates the three orbits controls here. The difference between this is between the two is what will actuate the operation of the individual orbit control systems. And this now will cause the propulsion of the antenna to the right direction for it to operate normally. So it's required that we understand the function of each and what the Earth station command signal is able to do. So the subsystem regulates The subsystem regulates the satellite in its orbit, regulates the satellite in its orbit, regulates the satellite in its orbit, and maintains stabilization and maintains stabilization and maintains stabilization and position of the soul of the antenna, and maintains stabilization and position of the antenna. Another thing is that we achieve this by use of sensors. This is achieved by use of sensors, which detects the low signal levels with reference to the preset, the rest of the preset values from the Earth station command signal, from the Earth station command signal. The difference is amplified and actuates the operation of the attitude control, the antenna control, and the orbital control circuits, and the orbit control circuits. The operation of either of any, the operation of any of the control circuits results in the propulsion equipment being driven in the required direction for correct orientation. So satellite link models are the parts or the different sections of the satellite for us to have a complete communication in a satellite. So there are basically three types of satellite link models: the uplink model, the repeater stations, and also the downlink model. Satellite link models are basically three. Roman 1, the uplink model, Roman 2, the repeater station, and Roman 3, the downlink model. So we're going to have the models and explain them in terms of diagram. For us to understand and have the correct picture from the basis of generation to the point where we are able to transmit, we need to have the diagram so that we explain it in terms of the required space. So we're going to draw the uplink model so that we understand what it is. So when we study this diagram, we're going to realize that we have got several units here that are involved in the Uplink model. And this one happens at the satellite Earth station. So the baseband is what we need to transfer or to transmit to the distant end. And it's basically from voice, data, and any other form of information required to transmit that is already converted into an electrical signal. So the baseband, the modulator here is modulates and confirms that into the required frequency. And after every modulation, there's normally the unwanted signals that are generated. And those unwanted signals that are generated are filtered by the bandpass filter. The bandpass filter is able to block the unwanted signals. So we go to the up converter. This up converter is what translates the frequency. This up converter is what translates the frequency to the required frequency for transmission in the gigahertz. So we're going to have the mixer and the microwave frequency generator. This microwave frequency generator is in gigahertz, and because the bandpass filter is also in megahertz, it converts that frequency into gigahertz. so that we are able to transmit at the satellite operational frequency. That one then again is passed through the bandpass filter to block any unwanted signals so that we do not amplify unwanted signals. The HPA stands for the high power amplifiers and is normally connected at the earth station transmitting end. The high power amplifiers convert the microwave frequency generated to the required power for transmission to the distant end. And because satellites start to move to cover a very large distance, we use the high power amplifiers to attain the maximum power required so that signal can be transmitted to the distant end. So we are going to have a bit of this. This is what is an HPA, an uplink model. There are several models, but this is the basic one as the most simplified one. And basically, it happens at the earth station transmitting point. So, the modulator converts the required, the modulator converts the baseband signal, converts the baseband signal into the required frequency, with the correct modulation index for transmission. The bandpass filter blocks all unwanted frequencies to avoid being translated and therefore prevents internal heating of the system. Other forms refer to as noise. The high power amplifier. We have the mixer, the up converter. The up converter. In brackets, whatever it comprises is the mixer, the microwave generator, and the bandpass filter. Converts the input frequency, converts the input frequency into the required microwave frequency. For transmission through the high power amplifier, HPA. Finally, the HPA provides the required power and amplitude so that the signal is transmitted to the distant end. Go to the repeater station, sometimes referred to as the transponder. Sometimes referred to as the transponder. From the term repeater station is a station whereby we are able to regenerate the signal to the required amplitude and frequency. So we are going to also to have this, to explain this with the aid of a diagram so that we are able to figure out the correct way possible. We're going to have the diagram. So when you look at this diagram, we have got the bandpass filter, which we now know its facts. And we're also going to do something referred to as the low noise amplifier, LNA, the low noise amplifier. And then again, I've got a bandpass filter. And there's a mixer and a microwave generator again. But there's also, from the microwave generator, there's something referred to as to other satellite transponder. Any satellite transponder or repeater station must have its own microwave generator. And because we might be having several repeater stations or several transponders in a station, then you try to generate with a single microwave, try to generate for other satellite transponders. That's why it's going to other satellite transponders. After every mixer, there's also a bandpass filter. And there's also an HPA, which we discussed in the previous diagram. So when you look at this, we get a signal from the Earth station, which is on a distant end. And the signal being weak, we first filter it because during the transmission process, it picked up the unwanted signals. Then we are able to filter it first, and the function of the low noise amplifier is not to amplify the signal into the larger magnitude, but it's to translate the signal into a low frequency signal. It's to translate the signal into a low frequency signal with lesser noise. With lesser noise, then we are able to pass it again through the bandpass filter, because during that translation, we generate other unwanted signal. We pass it again through the bandpass filter, and we go to the mixer now, where the low frequency signal is now improved again to the high frequency signal using the microwave generator. And when the translation occurs, then we are able to have the bandpass filter and the HPA improving the signal to the required power and all the way back to the transmission link. So this is what we refer to as a satellite transponder station. And this is what you require. So you normally require to understand that what does it do? It regenerates the signal and sends it back to the transmission line. So we could refer to it as a transponder. So the signal received goes through a bandpass filter which a bandpass filter which limits the noise applied, which limits the noise applied to the LA system, to the LA, to the LNA, to the LNA, brackets the low noise amplifier. The output of the low noise amplifier is fed to the bandpass filter again. The output of the low noise amplifier is fed to the bandpass filter again to remove unwanted signals generated. So the low noise also translates. The low noise amplifier also translates the high frequency signal to low frequency signal with very minimum noise. The output is then passed through an up converter that translates the low frequency signal to high frequency signal before being connected to HPA. We're going to connect to the high power amplifier HPA for correct power. So let us take note that each satellite transponder requires each satellite channel requires, each satellite channel, note that each satellite channel requires a separate transponder. So the downlink model. Downlink model. So we also have its own diagram. So this is basically what a downlink model is. And when you look at this, you are receiving the frequency from either a repeater station or an instance station. And that frequency is passed through the band pass filter. It's passed through the band pass filter so that we are able to minimize noise or limit the input frequency to the required amount before connecting to the LNA. The LNA now will translate the high frequency signal received to the low frequency signal received. And we translate that using the down converter for us to have the baseband signal as required output. So this is basically the reverse process of the uplink model. Because the only thing we have as a difference is the demodulator, which is able to give us, is able to reverse the process so that we get the baseband signal that require at the input. So we're going to have a little discussion on that. So the bandpass filter limits the input frequency to the required bandwidth. Limits the input frequency to the required bandwidth for the operation of the LNA. The LNA translates the high frequency signal. The LNA translates the high frequency signal to low frequency signal. To low frequency signal. To low frequency signal of the right power with minimum noise. The down converter then translates the low frequency signal to the required frequency for the demodulator. For the demodulator, so that the required baseband can be generated upon demodulation. JEMSHAH.